To begin, I would like to welcome you all to this brief webinar on advanced engineered nanomaterial exposure regimes for more realistic dosing scenarios on 3D liver models in vitro. My name is Samantha Llewellyn and I am an early career researcher from Swansea University. PATROL stands for Physiologically Anchored Tools for Nanomaterial Hazard Assessment and is an EU-funded project combining of a team of academics, industrial scientists, government officials and risk assessors from 24 partners across 13 different countries in Europe, North America and Asia. The mission is to deliver advanced and realistic tools and methods for nanomaterial safety assessment. So whilst the consortium as a whole will offer the following aims listed below, I will focus primarily on the development of 3D liver models for the in vitro toxicology assessment. With the principle to advance current in vitro test systems and to improve their physiological relevance, and based on the notion that 2D cultures do not fully encapsulate the intricate multicellular interactions and metabolic activity observed in vivo as well as 3D-based in vitro test systems, we began to develop a 3D cell line-based liver model. The aim of this work was to develop an accessible and realistic 3D liver model able to retain its proliferative capabilities whilst remaining viable for 14 days in culture. This was to allow for long-term and repeated ENM dosing regimes to be evaluated, whilst maintaining the ability to support genotoxicity endpoints like the micronucleus assay. As depicted by this diagram, our model itself is established using the hanging drop method to form 3D liver spheroids which consist of 4,000 HepG2 cells per spheroid and are approximately 500 micrometers in diameter. Over 3 days in culture, the hepatocytes should have assembled into compact spheroids ready to be transferred into the wells of the plate in preparation for chemical or nanomaterial exposure on day 4. So once we developed this model, we did some baseline characterization to see how the model performs and compares to other models on the market. We found the model remained viable for over 10 days in culture and was shown to maintain, if not increase, albumin and urea production throughout the 10 days in culture, highlighting that the model remains functional throughout this period. As with most spheroid models, the development of the necrotic core often limits the longevity of these proliferating models, as the larger and more compact the spheroid becomes, the harder it is for oxygen and nutrients to diffuse through. Some models, like the primary human hepatocyte models, offer a longer culture period as they are smaller, but then limit the evaluation of fixed DNA damage as they are non-dividing static models. So it does completely depend on the specific toxicity endpoints you wish to study. However, I shall take this opportunity to take you through the application of this particular 3D model, and the methodology behind building this model was published earlier this year in Jove and presented at the NanoSafe conference in November. If you have any further questions on this, please don't hesitate to contact me. Applications of this liver model have included general ENM toxicity screening, both with and without liver-resident macrophages, as well as mimicking more realistic dosing scenarios, the main focus of this webinar. So what does the liver see? With the liver being a secondary site of exposure for ENMs following systemic translocation from primary exposure sites, it is highly unlikely that the liver will be exposed to pristine nanomaterials, as interaction with a variety of molecules in varying compartments can transform the physicochemical properties of these materials. So to mimic this potential biotransformation, we built upon an SOP depicted here and devised by Angela Camphor and colleagues from the IUF. We added an additional 1-hour incubation in human blood plasma prior to further dilution in media and exposure onto the 3D liver spheroids. The objective of this study was to determine the impact of pre-treating nanomaterials with physiologically relevant simulant fluids prior to exposure on 3D hepatic cultures. In the 3D liver spheroid model, neither the pristine ENMs or pre-treated ENMs were shown to induce an elevated IL-8 response nor a significant increase in TNF-alpha release. In fact, compared to the negative control, there was a significant reduction in IL-8 following 24-hour exposure to both pristine silver and titanium dioxide, which could be indicative of IL-8 inhibition. However, this reduction in IL-8 was not as prominent with the pre-treated ENMs, which was shown to induce a higher concentration of IL-8 release relative to the pristine particles. This suggests that ENM transformation as a result of GIT pre-treatment schemes may have an effect on the biological interaction of silver and titanium dioxide ENMs and HepG2 spheroids. Following long-term exposure, however, the observed difference in IL-8 and TNF-alpha between pristine and pre-treated nanomaterials was no longer as defined. In addition, pre-treated silver nanomaterials induced higher TNF-alpha release in comparison to the untreated control, and a significant increase in TNF-alpha release compared to the pristine silver material following 24-hour exposure. The trend across both IL-8 and TNF-alpha response suggests that pre-treating the ENMs in GIT simulant fluids followed by incubation in human blood plasma did actually increase the release of pro-inflammatory mediators and could be influential in mediating an inflammatory response. IL-6 was also investigated, but all the results were found to be below detectable limits, and so the cytokine was not considered any further. Other biological endpoints were also analysed, and it was found that pre-treating ENMs did not significantly impede liver functionality nor induce elevated cytotoxicity or genotoxicity in 3D liver spheroids. So, in conclusion, the impact of GIT simulated ENM transformation upon toxicological outcomes at a potential secondary organ of exposure, such as the liver, have been demonstrated. A physiologically relevant tiered testing strategy to assess the biological effects of ENM transformation has been developed, and further work into independent toxicological effects of fractionated repeating ENM dosing will be further evaluated. So if you'd like to find out anything more about the project, the links to our website and social media platforms are listed here. Otherwise, I thank you for listening.